All right, welcome. Today we are cracking open the universe's rulebook. We're going to break down the three simple laws that control absolutely everything that moves, from your phone to a planet. This is everything you need for your GCSE Physics exam on Newton's laws. Let's do it. So, let's kick things off with a bit of a mystery. Picture this. You're on a field, you kick a football. What happens? It rolls for a bit, slows down, and then just stops. Yeah, seems totally normal, right? We see it all the time. But why does it actually happen? Because then you look up at space. A satellite or even just a random rock floating out there can just keep going and going and going forever at the same speed in the same direction with no engine pushing it. So what is the deal? Why the massive difference? Well, the answer to both questions comes from one guy, Sir Isaac Newton. And the secret all starts with his first rule, which we're going to call the law of laziness. Honestly, it's a great name for it, because it turns out that everything in the entire universe is, deep down, fundamentally lazy. Okay, here's the official version you'll want to remember for your exam. The key phrase here is resultant force. That's just the overall force when you add up all the pushes and pulls on an object. If all those forces cancel each other out, or if there are no forces at all, then the object just keeps doing whatever it was already doing. It's too lazy to change. So this law of laziness works in two ways. First, if something's not moving, it'll stay not moving. Think about your character in a video game when you put the controller down. It just stands there, right? It won't move an inch until you, the force, make it. And second, if something is already moving at a steady speed in a straight line, it'll just keep on doing that. It won't speed up, slow down, or turn unless a force gets involved. Right, exam question alert. This is a classic trap they love to set. So, the moon orbits the Earth at a more or less constant speed. So, is that an example of Newton's first law in action? What do you think? The answer is a big, fat no. And you have got to remember this. Velocity is not just speed. Velocity is speed, times, and direction. And because the moon is constantly curving in its orbit, its direction is constantly changing. And if the direction is changing, the velocity is changing, which means a resultant force has to be acting on it. And that leads us perfectly into rule number 2. So if a force comes along and messes with an object's lazy state, what happens next? How much does its motion actually change? Well, that's exactly what Newton's second law tells us. Let's call it the push and shove law. Okay, this definition sounds way more complicated than it is, I promise. It really just means two very simple common sense things. One, the bigger the push you give something, the more it accelerates. Duh. And two, the heavier something is, the more mass it has, the harder it is to get it to accelerate. And all of that, the whole entire law, boils down to this one beautiful, iconic equation, F equals ma. Force equals mass times acceleration. Seriously, this equation is a superstar. If you're going to tattoo any physics equation on your brain for the exam, make it this one. And you see this in action all the time. Imagine you're at the supermarket. You give an empty trolley a little push and whoosh, it shoots off, right? Now imagine that trolley is loaded up with a week's worth of shopping. You give it the exact same push, and it barely moves. Same force, bigger mass, much smaller acceleration. That is F equals m right there. Okay, so we've got a law for when things stay the same and a law for when things change. The third and final law is a bit of a plot twist. It turns out no force in the universe ever acts alone. Every single push has a push back. Welcome to what we'll call the cosmic comeback law. This is Newton's third law, and you've almost definitely heard it before. For every action, there is an equal and opposite reaction. It means exactly what it says. If you push on a wall, the wall pushes back on you with the exact same force. If you lean on a table, the table pushes back up on you. Every single time. No exceptions. Now listen up, because this is probably the biggest point of confusion in this whole topic. A book on a table has balanced forces. That's the first law. Gravity pulls the book down, the table pushes the book up. Those are two forces on one object, the book. They cancel out. The third law is different. It's about the interaction between two objects. It's the book pushing down on the table and the table pushing up on the book. See the difference? Two forces on two different objects. Now, you don't just have to take Newton's word for it, or mine for that matter. You actually get to prove F equals ma for yourself in one of your GCSE core practicals. So let's quickly take a look at how that actually works.
So the setup is pretty simple. You've got a trolley, and it's attached to a string that goes over a pulley and has some weights hanging on the end. Those falling weights provide the accelerating force. The mass is just the mass of the trolley itself. And you can measure the acceleration by timing how long it takes to cover a certain distance. By changing the weights to change the force, or adding masses on top of the trolley to change its mass, you can see for yourself that F equals ma really works.
Okay, so now that we're experts on these laws, let's use them to clear up one of the biggest mix-ups in all of physics, the difference between weight and mass. And trust me, they are absolutely not the same thing.
So what's the difference? Well, your mass is the amount of stuff you're made of. It's measured in kilograms, and it's the m in F equals ma. It never, ever changes, no matter where you are in the universe. Your weight, on the other hand, isn't stuff at all. It's a force. It's the force of gravity pulling on your mass. And because it's a force, it's measured in newtons, and it can definitely change. Let's put some numbers to this. Let's say your mass is 50 kilograms. Here on Earth, the pull of gravity gives you a weight of 490 newtons. But if you took a trip to the moon, where gravity is much weaker, your weight would only be a floaty 82 newtons. Your mass, the amount of you, is still 50 kilograms, but the force pulling on you is way less. And for our last stop, let's circle back, pun intended, to that moon problem from the beginning. We figured out it must be accelerating because its direction is always changing. So what's the force that's actually pulling on it and causing that acceleration? Well, this takes us into the world of circular motion. You see, to make anything move in a circle, you need a force that is constantly pulling it towards the center of that circle. It's called the centripetal force. Without that constant inward pull, the object would just obey Newton's first law. It would be lazy and just fly off in a straight line. Now, centripetal force isn't some new magical force that just appears. It's more like a job title, and that job is always done by a force we already know. For the moon orbiting the Earth, the centripetal force is provided by gravity. When a car turns a corner, the job is done by friction between the tires and the road. And if you swing a conker on a string, it's the tension in the string that's doing the work, pulling it inwards. So there we have it, the three laws that literally run the entire universe. Rule 1, the law of laziness. Objects just keep doing what they're doing. Rule 2, the push and shove law. If you want to change that, you need a force, and F equals ma tells you how. And Rule 3, the cosmic comeback law. Every single force is just one half of a pair. And I'll leave you with one final brain teaser. When you're in a car that's turning a corner, the centripetal force is pulling the car inwards. So why does it feel like you're being pushed outwards into the door? Well, the answer is Newton's first law. There is no outward force. Your body is just trying to be lazy and keep going in a straight line, but the car is turning into you. Think about that next time you're a passenger.